So on today's class, we are going to study the recurrence relation for first recurrence relation for Bessel function. So the recurrence relation or formula for Bessel's function. All right. So the first relation says x j n dash x is equals to n j n x minus x j n plus 1, where jn x is summation r tends to 0 to infinity minus 1 upon r upon factorial r factorial n plus r x upon 2 n plus 2r. Alright, so this is the first recurrence relation we need to prove. If I just multiply x with the first derivative of jn, this will give us n multiplied by jnx minus x jn plus 1x. Alright, so just to derive this one, we will use the left hand side. So proof is, we know gnx easily as what? Summation r tends to 0 to infinity minus 1 upon minus 1 raised to power r factorial n plus r x upon 2 to the power n plus 2r. So the first derivative, so this is equation 1, differentiating equation 1, differentiating equation 1 with respect to x. So this will give me what? I can write jn dash x or prime. This means the first derivative of jnx is equals to summation r tends to 0 to infinity minus 1 to the power r factorial n plus r. So the first derivative, if we differentiate x upon 2 to the power n plus 2r, this will give me here n plus 2r, and here x upon 2 to the power n plus 2r minus 1, and 1 into if we differentiate x upon 2s, so this will give me 1 upon 2. Good. Or we can remember it, x to the power, differentiating x to the power n, this give me n x to the power n minus 1. So this for what we use here already. So say this is equation 2. Now multiplying, we need one additional term, what? X with jnx, multiplying x to equation 2, sorry. So this will give me x j dash nx is equals to, okay, if I separate all the term with n and 2 plus r, so this will give me n is constant, so there is no relation for summation, so I can take it out. So now r tends to 0 to infinity minus 1 upon r factorial n plus r, here 1 upon 2, and we had multiplied x, so x upon 2 we have an additional term x upon 2, and if we see x upon 2 n plus 2r minus 1, so this will give me x upon 2 to the power n plus 2r. Alright, one additional term was x upon 2 plus x, what did that we had multiplied in, so just I had written in front of summation r tends to just infinity, 0 to infinity, minus 1 to the power r factorial r factorial n plus r. So the left quantity was 2r here, and one additional term to this term, and x upon 2 to the power n plus 2r minus 1. Alright, so we have x multiplied by this. So if I look closely, this is nothing but jnx, so I can write it as n jnx plus x summation minus 1 to the power r. I can write it as what? If I remember, factorial r equals to r minus 1 factorial. Alright, so if I need to calculate the value of what, this factorial r can be written as 2 r minus 1 factorial, here 2r x upon 2 to the power n plus 2r minus 1. Good. Now r cannot take the value of 0. Why? Because if I take the value of 0, so the factorial, this term becomes minus 1. So factorial can't be negative. Just we need to put the value of r equals to 1 to infinity. Alright, so this will cancel out, r2 also cancel. So the final result will be n jnx plus x multiplied by r tends to 1 to infinity minus 1 to the power r upon factorial r minus 1 x upon 2 to the power n plus 2r minus 1. Just substitute, put r minus 1 as s. So r will give me s plus 1. If r is 1, s is 0. If r is infinity, s will also infinity. So just substitute this in upper equation. N jnx is equals to n jnx plus x summation s tends to from where to 0 to infinity, 0 to infinity minus 1 r, the value of r is s plus 1 upon factorial r minus 1 as, okay, we had missed one term here, n plus 2r. We will have one term factorial n plus r, here we'll have n plus r. So r minus 1, factorial r minus 1 will be as factorial s, n plus r, the value of r is s plus 1. Alright, x upon 2 to the power n plus 2 multiplied by r, the value of r is r plus 1 minus 1. So you can write it as n jnx plus, okay, if I take minus 1 outside of this summation, so the quantity becomes summation s tends to 0 to infinity minus 1 to the power s upon factorial s. I can write this as factorial n plus 1 plus s, and I can write this as x upon 2 as n plus 1 plus 2s. Alright, so if I see this term, so this is nothing but n j and x is same as this minus of x. This is what, j n plus 1x. Alright, So this was the first recurrence relation. X j dash nx is equals to njn x minus x jn plus 1 x. So this is the first recurrence relation. Alright. We have a question. A numerical says prove that limit x tends to 0, limit x tends to 0, jnx upon x to the power n is 1 upon 2 to the power n factorial n plus 1, where n is greater than minus 1. Alright, so this we need to prove. So I know the solution will be, if we remember, jnx can be opened as x to the power n in series form to the power n factorial n plus 1. Sorry, this is gamma n plus 1. Bracket start 1 minus x square upon 2 2n plus 2 plus x to the power 4 2 4 2n plus 2 2n plus 4 minus 1. I had taken the direct result because when we have solved the differential equation solution for Bessel function, we have already derived this relation. Alright, so if you have any problem in this relation, please do check our differential equation of Bessel function lecture. So on taking limit both the side when x tends to 0. Alright, so limit, say x tends to 0, and I just multiply x into this denominator, so this will give me gnx on x to the power n 1 upon 2 to the power n gamma function n plus 1 1 minus x square upon 2 2n plus 2 plus x to the power 4 2 dot 4 dot 2n plus 2 2n plus 4 minus so on. Alright, so if we take the limit x tends to 0, okay, just right here gnx upon x to the power n is equals to limit x tends to 0. So this will give me, all these term will be vanish out, this goes to 0. So the only left quantity becomes limit x tends to 0 gnx upon x to the power n will give me 1 upon 2 to the power 1 function n plus 1. So this is what we have to prove. Okay, so this is the recurrence relation and the numerical on Bessel function. Thank you.